Hello. So if you need to, you should have had a look at the video on basic correlation and regression, and you should be fine with linear regression, how to find the equation of a regression line from the raw data on your calculator, and also how to find the PMCC of raw data using your calculator. As long as you can do that, everything that follows afterwards is just logs. The logs that you already know from your core math logs. So when you haven't got data which in its raw form is linear, sometimes if it's exponential, you can use coding to make that data linear, so you can use linear regression before you then reverse the coding to work out other things. So sometimes you code both variables, so you would code the x and you would code the y to make it linear. Other times you would only need to code the x or only need to code the y. So the two ones you need to be familiar with, and I've lifted this straight from the book, are data in the form y equals ax to the n, which is coded where you code both, so you code the y and you code the x, and also this form here, data in the form y equals kb to the x. In this instance, you code the y, but you don't need to code the x. So the difference between the two is here, the x is the power, and here the x is the base number. But both of those can be coded. They're both exponential models, and they can both be coded using one of those two forms there to turn it linear. So the example I'm going to show you here, and hopefully I've fitted that all on, is this one, and I've just lifted it from the book. And I don't really want you to get too tied up in this. If you want to read through it, please press pause and have a read through, but there are better ways for you to do this than to learn these rules off by heart, but I will just talk you through it briefly. So this data here is of the form y, it's exponential, it's of the form y equals 0.1 x to the 1.8. So it's this form up here, y equals ax to the n. The x variable is the base number, not the power in this instance. If we coded it by taking a log of y and calling it big Y and log of x and calling it big x, we'd end up with this data, which could then be plotted, and you would have a linear model here, a straight line. The gradient of the straight line is 1.8. If we go back up to here, the gradient would be the n value here. So the gradient is 1.8, which means n is 1.8, and n is the power, which is exactly what we've got here, 1.8. If we look at the y-intercepts, if we go back up here, the y-intercept would be log a. The y-intercept here is -1, so log a is -1. If we inverse log both sides, write them both as powers of 10, we get a equals 10 to the -1, so a equals 0.1, which is exactly what we've got here, so what we would expect. But I would really prefer you not to learn these rules and just to use your log laws instead. It's going to be this one or this one. You can use your log laws to work out the values of a and n, or to work out the values of k and b. It's much more efficient than wasting time learning a rule that you don't need to know. So if we look at this example here, which is the example, actually I'm going to take that out, hang on a sec. It's a bit shiny. Hopefully that's better. So here's the example that I've taken straight from the textbook. So you don't need to know, and you will never need to know. You'll never need to choose which coding. They'll always tell you the coding to use. So it's about the temperature T. So please notice that T is the original variable, and growth rate G. So T and G are the original variables that you've got. Here's a chart of the temperature and the growth rate here. It's coded using x equals t and y equals log g. And the regression line is found to be y equals negative 0.2215 plus 0.0792x. So all of that data is given to you there. Mika then says that the constant in the regression line means the colony is shrinking when the temperature is 0. Explain why he's wrong. Well, what he's done, presumably, is he said that when the temperature, so when t is 0, x is also 0, he's put 0 into there, so this is 0, and he's found that y equals negative 0.2215, so because it's negative, it must be shrinking. But what he's done there is he's looked at y And he said the colony is shrinking, the growth rate is shrinking because y is negative when t equals 0. But y is not the growth rate. G is the growth rate. So you always need to, before you make assumptions, or before you draw conclusions, to relate it back to the original data. So what he would need to do here is reverse the coding and see what happens to the original data. So we'd have this regression line here. When x equals 0, it's exactly what we'd said. We said y equals negative 0.2215. We know that y is log g. So log g, swapping y for log g, is negative 0.2215. To inverse the log, we write them both as powers of 10, which is what's happened here. Those two will cancel out and leave you with g. And 10 to the power of negative 0.2215 is positive 0.6. So the growth rate, G, is actually positive, so the colony is increasing and not shrinking. So just the point to take away is just remember you always need to reverse the coding every time. And this is the bit about logs which I really wanted us to do together and for you to be familiar with doing it this way rather than just learning rules. So given that the data can be in actual fact, I wouldn't even, let's just disregard that. Let's just say we know this. Can we use this coding to get the data back in its exponential model, regardless of which form it takes? So we know that y equals negative 0.2215 plus 0.0792x. And we know that the data was coded using x equals t and y equals log g. So we need to put those back because we were going to reverse the coding now. So y is log g equals 0.2215 plus 0.0792x, which is t. So we've put the original variables back into the equation and we can work on it from here. So to get rid of the log, we need to write both things as the power of 10, which I'm going to cheat a little bit and just put them down there. So if I make that big equals, so I've written them both as the power of 10. Those two will cancel out and leave me with g. And on this side, I've got 10 to the negative 0.2215 plus 0.0792t. So this is all the same power of 10. Everything that you do from here is just your GCSE indices laws. So you know from GCSE indices, if you add the powers, what you're actually doing is timesing the numbers. So I can timesing the numbers. So I can rewrite this as 10 to the minus 0.2215 times 10 to the 0.0792t. Because when you times numbers at the same base, you add the powers, so we're just going backwards. This you can work out. I'm just going to cheat because I don't know where my calculator is. Oh, I should have known that from before. So if you work this out, it's 0.600, and I am going to leave them to 3 decimal places for now. And this we still need to work on. So if you think back to GCSE, you know that if you times the powers, what you've done is raised one power to a further power. So I could rewrite that as 10 to the 0.0792 all to the power of t. Because if you raise it to another power, you times the powers, which is exactly what we did up there. This is a number which you can work out. I'm going off the page a little bit. If you work this out, excuse me while I cheat, 1.20 to the power of t. So there you go. We've found out it's of the form g equals k b to the t. K is 0.600 and b is 1.2 or 1.20. So 3 significant figures each. It wouldn't matter. It's told you it's that form, but it wouldn't matter if it was the other form, because when you worked through the question using your logs, you'll see which form, it will automatically turn out to be one or the other. So please try to use your log laws and your index laws to work out which form it is and to work out the values of the constants. rather than learn those rules that were on the first page. So hopefully that will clear up where that comes from. And always remember that if you're going to make an interpretation, you need to reverse the coding and get back to the original data before you interpret what you found. And that's really the only extra bits for exponentials. Everything else is the easy, straightforward stuff that was in the basics lesson before this.